In this video, we're going to talk about logarithm functions. I always start my conversation about logarithms with an exponential function because exponential functions and logarithmic functions have a very special relationship. So here's a very generic exponential function, right? I haven't given you any specific number for the base. I'm just going to keep the variable there for the moment. Remember in the last couple of videos we've been talking about these functions, and at some point we've looked at the graph. Let's just say that this one is representing exponential growth. So the graph has a shape sort of like this, or maybe it's reflected the other way, so it's decay. Is it one-to-one? So one-to-one function, to be a function, it passes the vertical line test. To be one-to-one, it must also pass the horizontal line test. Even though it's very flat over here on the left-hand side, it is consistently decreasing, getting smaller and smaller and smaller. It's hard for us to see, but it's true. So it does pass the horizontal line test. It is one-to-one. If we're sort of integrating a lot of things we've talked about over the last few weeks. So if it's one-to-one, then it does have an inverse. The inverse of an exponential function is a logarithmic function. Okay, so if we went through the natural process we've been using to find the inverse, again, I know this is a generic function, but we're going to go with it for right now. The first step would be to put in the y. We already have that. The second step would be to exchange the x and y in the equation. So where there was a y, we're going to put in an x. Where there was an x, we're going to put in a y. And then we would solve for y. You can think about all the mathematical operations that we've practiced up to this point that we could use here maybe to solve for y. Usually what comes up to our mind first probably is some kind of a root, a y root or something like that, okay? But even if we did that, really that's going to be solving for b, not for y. So we could think about all the mathematical tools we have. We don't have a tool yet that solves for the exponent. So we're kind of in a quandary, okay? So what does solve for the exponent is a logarithm. That's its job. So a logarithm is an operation, that's a pretty key word in this sentence, that solves for the exponent. So a logarithm is sort of like a plus or a minus or a square root. It's an operation that allows us to isolate the exponent, which is something we haven't done up to this point. And there's lots of ways to think about that. I want to show you a couple perspectives that we can use to understand the logarithm. The first one is to convert between these two formats. So we have what's called the exponential form, and this is exactly what we have written here, where we have y as the exponent. Okay, and this sentence is true if and only if this other sentence is true. So basically I can go back and forth between these two formats, and I can use that as sort of a definition to help me understand what the logarithm does. So I can rearrange the parts that I have here, and I can rewrite it as a logarithm. B here is called the base. And so the base becomes the subscript on this word log that represents the logarithm. The base describes what type of logarithm I have. So just so you can get a good idea, this reads the log base b of x. Okay, so the b there, I probably could have spaced it better, is a subscript for the word log, and it's specifying what type of logarithm I'm talking about. Okay, so the log base b operates on x basically it's saying, okay, if b is my base, x is the result that I get, what exponent must have been applied? And y here is my exponent. That's the basic idea of the logarithm. So let's practice going back and forth between these two formats. Really, this just amounts to us rearranging those three parts: the base, the exponent, and I call it the result. It's not really maybe a formal name, but that's what I'll use. Okay, we're not doing any solving here. We're just rearranging parts that look like this into a logarithms sort of way to organize it, and vice versa, back to the exponential. Okay, so let's say I have an exponential sentence like 3 squared equals 9. This is a fact, okay? I can also represent this fact in a logarithm format. So kind of identify what's what, right? 3 here's the base, 2 is the exponent, 9 is the result that I get. So if I want to rewrite this as a logarithm, it'll be a logarithm base 3 of the result, which would be 9. So 3 raised to what exponent is going to give me 9? 2 is my exponent. When I write it as a logarithm, the exponent part is always by itself, because that's what a logarithm does. It solves for the exponent. Okay, we could do the same thing here with e to the x equals 20. So e is my base, so I'll have a log base e of the result, 20, must be equal to the exponent I have, which in this case is an x. Okay, so I'm just taking those three parts and rearranging them into a logarithm. Now, if you have experience with logarithms, you know that log base e is a very special logarithm. So you could go ahead and write that as a natural logarithm if you're comfortable with that. We're going to get to that in a minute. If you want to go there now, that's fine. I'm not going to go there yet. Okay. All right, now let's practice the other direction. Let's say I have a logarithm, but I would really prefer to rewrite it as an exponential. So same thing, I want to identify the base, the exponent, and the result. I have log base 4 of 16 equals 2. So 4 is my base, 2 is my exponent, and that must be equal to what's inside, which is the 16. That's the result. Okay, last one. I have the log base a of 4 equals 5. So I could rewrite this as well. A is my base, raised to the exponent of 5, must be equal to what's inside, which is a 4. Okay, if you like this viewpoint, you can do everything we're going to do with logarithms by just using this conversion idea. It seems really simple, but it can go very far. You can solve equations, you can make graphs, you can do everything we're going to do with logs by doing this. Okay, some people like to do this conversion process, some people don't. So let me show you an alternative perspective. Obviously these tie together very closely, but it is a little bit different, so let me show you what that looks like. So this second perspective, I call it canceling the base. Okay, so remember we said a logarithm allows us to solve for the exponent, and we said that a logarithm function and an exponential function are inverses. So if we put all of that together, the idea that they're inverses means that a logarithm and an exponential function, the operations that they carry out, which are not like the traditional operations of addition, subtraction, multiplication that we're used to seeing, but It's an interesting type of canceling, and they counteract each other, and there's some canceling that happens that allows us to solve for the exponent. Okay, so we can see that here. So if I have the log base 10 of 10 to the power 1, the log base 10 and the base of 10 cancel each other out. Like I said, it's a new and interesting type of canceling. It's not something that we're used to seeing, but they do counteract each other. You could definitely plug this into your calculator, do the things that you need to do to prove it to yourself that this kind of canceling is happening. That's okay and normal, okay? You don't have to trust me. Test it out. Make sure that I'm not telling you a lie. Okay, so we could do the same thing here, right? Log base 10 of 100. Maybe it's easiest to see if we write 100 as a power of 10. So 100 would be the same as 10 squared. 10 times 10. The same kind of canceling, right? The base of 10 and the log base 10. These are opposite operations, and they cancel each other out. And we're able to solve for the exponent. How about log base 10 of 1,000? If we wrote 1,000 as 10 to an exponent, it would be 10 cubed, or 10 to the third. The base of 10 and the log base 10 will cancel, and we'll be left with just the exponent. What about 1/10? This one's a little bit of a stretch. I'm pulling on your properties of exponent knowledge. Okay, but 1/10 is the same as 10 to the negative 1. Remember, a negative exponent brings what I'm applying it to down across the fraction bar. This time, in case that would be down into the denominator. So these are the same. And then I can do that same kind of canceling to get the exponent by itself. Okay, one more. How about the log base 2 of 8? So I can write 8 as a power of 2. That's 2 cubed. So this type of canceling only works if the base and the log with that base, right? That base of the logarithm and the base of my expression here are the same. If those aren't the same, then it's not going to do that nice canceling that we're hoping for. But there are some tricks that we can use to make it match. Okay, so maybe that this is a perspective that you like. Canceling the base is something that you can use, right, to do all the things that we're going to do with logarithms, solve equations, make graphs, all those sorts of things. Okay, so let's take a second to look at a graph of a logarithm function. I always like to start with the exponential function so you can see how they are related. And by thinking about the exponential function, I have an easier time graphing the logarithm function. So I usually give you these together just to make it easy for you. But, you know, that may not always be the case if you go on to other classes. So you do want to kind of identify how the graph of the logarithm function is related to its exponential partner. So let's start, and let's do 2 to the x and log base 2 of x. Notice these are inverses because the base of the logarithm here matches with the base of the exponential function. It's always the case. We graphed this function, or something similar to this, in a previous video. So we can use the standard set of x values that we've used in the past. For this function, remember we're putting our x values in as the exponent on the base of 2. So if I'm plugging in 0, that's 2 to the 0 power. Anything to the 0 power is 1. This would be, if I plugged in 1, this would be 2 to the first. and then 2 squared. Okay, here comes the negative exponents again. So 2 raised to the negative 1 power would be 1/2. And 2 raised to the negative 2 power, it's going to do that reciprocal and square it. So it's going to give me 1/4. Okay, so if I plot those, I have 0, 1, 1, 2, 2, 4, negative 1, 1/2, and negative 2, 1/4. Okay, notice my base here is 2, which is a number bigger than 1. And so as I look from left to right, my graph is increasing. If we kept going with this, the increase would continue to be more and more rapid. Right? It would go up faster and faster. Okay, now because the logarithm function is the inverse, we can most definitely take these points and flip them around, just like we talked about when we were practicing with inverses. Okay, and in general, if I'm making a logarithm graph, powers of the base here is 2. So any power of 2 is going to make a convenient x value choice, because my y value will then come out to a nice round number. Okay, so I'm going to use these y values because these are powers of 2. I'm going to write out the logarithm so you can see. As we go through the rest of this video, we are going to add skills as far as how to calculate the logarithm, either in our head or with our calculator. So that'll make this part maybe a little more concrete. But for now, I'm going to rely on what we know about inverses, I guess, the most. Okay, so if I didn't just fill in the x values that I know are going to pop up here for my y's, maybe I plugged these in. So the log base 2 of 1, the way I could evaluate that is I could think, okay, 2 raised to what power is going to give me 1? And I know it's 2 to the 0, right? Same thing here. I could think 2 to what power is going to give me 2? And it must be 2 to the first power. And then here, 2 to what power is going to give me 4? It's 2 squared. When I raise 2 to the negative 1 power, that's what's going to give me that 1/2. And when I raise 2 to the negative 2 power, that's what's going to give me the 1/4. Okay, so now that I've done that, maybe I've thought a little bit about how the logarithm calculates the y value. I can plot these points. So the logarithm graph, if there's no number in front of the logarithm, 1, 0 is always going to be a point. We've got 2, 1, and 4, 2. I also have 1/2, negative 1, and 1/4, negative 2. Okay, and we've talked a lot about how the inverse is a reflection. So that's happening here as well. The logarithm graph would be the red graph, right? The exponential graph is the blue graph. So I have graphed these together. Both of these are not the logarithm graph, right? Only the red one. So if you wanted to just graph the logarithm, you would just have this red curve. Okay, and there are some opposite things about the logarithm and the exponential function. Notice the exponential function is rapidly increasing. The logarithm function is increasing, but more gradually as we go to the right. Okay, so they're opposite in that way. It's a gradual increase. The graphs are reflected over this diagonal line because they're inverses. This is that line y equals x. Okay, and I've tried to summarize some of that below here. So this is a function, a logarithm function is y equals log base b of x. Notice for the red curve, the y-axis is a vertical asymptote. We said an asymptote is a line that the graph approaches but does not cross. It gets infinitely close to the y-axis here as it goes, as x gets smaller and smaller, the y value gets lower and lower, but it never touches the y-axis. The next one says that the graph is a reflection of y equals 2 to the x over that diagonal line that we've drawn. Okay, and then we can list the domain and range of this logarithm graph. Notice, I'm going to keep the picture up here, so I'll just write it up here in the corner so I can get everything on the screen. Notice from left to right, just the red curve. I'm not touching the y-axis, which is where x is 0, but I am infinitely close to it, so all positive values. The logarithm cannot operate on a negative value. And that goes back to our definition of the base for an exponential function. So related to that. Okay, and then the range on my arrow down here at the bottom is going all the way down to negative infinity. And as I go to the right, this arrow is going to continue to increase more and more and more up to positive infinity. The range here for the logarithm function is the exponent, and the exponent can be positive or negative, anything. So all real numbers for the range. Okay, now we kind of just did this evaluating idea a minute ago. One thing at a time. Okay, so you can use the converting idea if you like, or you can use the canceling the base idea. Either of those would apply here, right? Either way, I want to think, okay, 2 to what power is going to give me 16? And then I would want to rewrite 16. Okay, I'm going to try to incorporate both here, right? Both viewpoints. So 16 would be 2 times 2 times 2 times 2, right? 4 2's. Think about it. So the base of 2 and the log base 2 will cancel. And 4, right? It's 2 raised to the 4th power is what's giving me 16. All right, I hope you can see both viewpoints in there. It's really hard to give time to both, but I'm trying my best here. Okay, if we wanted to evaluate this logarithm, and we're doing this in our head, we're going to talk about how to do it in a calculator in just a second. So 1/3 raised to what power is going to give me 9? This is a thinker, all right. So I need to do a reciprocal here. I need to flip that fraction over to make it 3. A negative exponent is going to do that, right? And I also need to square that 3 to make 9. So the exponent I'm looking for here is -2. So it's 1/3 to the -2 power. That's what makes 9. And so here's the canceling the base idea. These two cancel. Or you could just think 1/3 raised to the -2 power is giving me 9. Okay, how about the log base 4 of 1? What's the exponent we're dealing with here? Zero, right? 4 raised to the 0 power is what's going to give us 1. Okay, so this is a way we could evaluate logarithms just based on our knowledge of math, exponent facts, okay? Now let's take a second to talk about how we can put a logarithm into the calculator. There are 2 logarithm buttons on your calculator. The first one is called the common log. It's base 10. So if a logarithm is written without a base, it is implied that the base is 10. So if you see just log of x or log of 500, the base there, if it's not written, is an implied 10. And that's the log button that you see on the calculator. The second type of logarithm that's on the calculator is called the natural log. This one is base E. We've already talked a little bit about the natural log in previous videos, but this will give you maybe a better sense of what it is. So this is a log base E. So although it's totally fine to me if you write log base E of x or some number, the more conventional way is to rewrite this as an ln of x. ln is Latin, so it's logarithm natural, okay, which is why the L comes first. But this is also a button on your calculator, the ln button. Okay, so let's come back to this. Let me do a couple examples. I'll just add them at the bottom here. If we wanted to calculate the log base 10 of 6, we would use the log button to do that because it's base 10. So we would hit the log button, log of 6. All right, we don't see the 10, but remember we said if there's no base listed, it's implied to be 10, and that's true for the log button. So here's the log base 10 of 6. We'll round it to 3 digits, 0.778. Okay, let me give you another example. Let's say we wanted to calculate the natural log of 2. Okay, same thing. This is a base E. It's not written there, but it's implied. So we would use the ln button, which is just below the log button. So we can do ln of 2. And same thing, we'll round to 3 digits, 0.693. So what that means is 10 raised to this power. It's not coming out even because 6 is not a power of 10. 10 raised to the 0.778 power would give me 6. E, which is not written here, but it's implied, to the 0.693 power would be 2. Okay, so what if I need to evaluate a logarithm that is not base 10 or base E? You have 2 options. You can either use what's called the change of base theorem, which I want to show you what that looks like. It forms a ratio. You could use that to calculate it. Or, and I kind of regret this, I don't have this on my calculator, but for those of you with newer calculators than mine, I need to update mine. Under the math button, if you scroll all the way down to choice A, I'll show you, but I don't have choice A. Okay, it's below 0 would be choice A. It's called the log base, and that will allow you to, what it does basically is gives you the log with these little dotted boxes, and it will allow you to fill in the base and the what the logarithm is applying to so that you can calculate. It's a very handy tool. If you don't have that, if your calculator is older like mine, you can get an update, and probably the folks in the Math Center could help you with that. Okay, so those are your two options. I want to show you the change of base theorem. I'm sorry I can't show you this log base, but you should definitely take your calculator and check to see if you have that and try it out. It's probably the best, simplest, we'll say, way to go. Okay. The change of base theorem looks like this. So this allows you to take a logarithm and rewrite it with any base. Okay. A would be the old base and B would be the new base. Okay. So if I have a logarithm that looks like this, but I want to calculate it, but it's not base 10 or base E, I can rewrite it as a ratio of logarithms. It sounds far more complicated than it actually is. Okay, so let me demonstrate it for you because that's a lot easier to see. Let's say we wanted to do log base 6 of 18. 18 is 6 times 3, but it's not a power of 6, so it doesn't come out nice and even. Okay, so to calculate it in our calculator, we have two buttons. We have the log base 10 and the natural log, so you could use either. If you do the log base 10, you'll take the log of 18 divided by the log of the previous base, which was 6. Okay, and so let me show you what that would look like. So if I do the log of 18, I need to make sure that I close the parentheses here. If you don't close the parentheses, it will not calculate it correctly. Divided by the log of 6 gives me 1.613. Okay, and just to show you that this works with both options, you could also use the natural log because that's a button on your calculator. Some people prefer the natural log. It's just a matter of preference. It's not really anything that's more convenient, but you could do the same thing. So do the natural log of 18. Again, close the parentheses. Divided by the natural log of 6. Same answer. Right. The individual logs evaluate differently, but the ratio is the same. So you can use either one. Okay, I need to wrap up because this is getting long, but here are some uses for the change of base theorem. We just looked at evaluating a log that is not base 10 or base E. You can also graph a logarithm function on your graphing calculator, and when we look at equations, we will you can use this as well, right, to evaluate a logarithm with a different base. Here's how you would type this into your calculator. So if I wanted to graph the log base 2 of x, like we just did on paper, I could use the change of base theorem to type it into my calculator. Again, if you have the log base, you don't have to use this, but if you don't, then this is a good tool for you. So I could do the log of x divided by the log of 2, and this is how I would graph 2 to the x. So this should look very similar to the graph we just made by hand. All right, hopefully that gives you a lot of information about logarithms. They're challenging because they're a new way of thinking, so I want to challenge you to dive in and work with them and practice. Choose a perspective, either the converting or the canceling the base, and work with that as much as you can in the next week or so as we practice things. All right, best of luck to you.